Ready for a wild one? We're diving into AI and geometry.
AI and geometry sounds a bit abstract.
Not at all. We're going to break down how this system, it's called AlphaGeometry, is solving problems, like crazy complex geometry problems.
Oh, okay, like the kind you'd see in those math Olympiads.
Exactly. The ones that make even like the smartest people scratch their heads.
Right, those are really tough. I've heard that teaching AI to do geometry is surprisingly difficult.
Yeah, you can't just like feed it a bunch of formulas, right?
It's not just about formulas. It's more like you need to teach it to think, to actually see the relationships in shapes and angles, you know?
Yeah, it's almost like explaining a joke to a robot. The nuance, it just gets lost.
And for the longest time, that's what held AI back in geometry.
They had to rely on us humans to like spoon feed it proofs and stuff.
Exactly. And let's be real, that's not really efficient, is it?
About as exciting as watching paint dry, for sure. But this new research, this is where it gets really interesting. This alpha geometry thing, it's breaking the mold.
It's actually creating its own data. Huge amounts of it. It's generated over 100 million synthetic theorems and proofs. Can you believe that?
Wow, 100 million. That's more than, I don't even know what to compare that to. Okay, but how does it even start? Are we talking like proofs that are longer and more complex than what you'd find in a textbook?
Think even more complex than actual Olympiad problems. That's the level we're talking about.
Seriously. So how does it do it? It's like the AI equivalent of those math geniuses. You know, the ones who just seem to pull solutions out of thin air.
It's a two-part system, kind of like a dynamic duo. First, you have what's called a symbolic deduction engine, DD plus AR for short.
DD plus AR.
Catchy. Right. Think of it like, imagine a superpowered geometry textbook filled with every rule, every axiom you can think of. That's part one.
Okay, so it has all the rules. Got it. What's the second part?
Part two is the language model. This is where it gets really cool. The language model learns from all those synthetic theorems and proofs.
So it's like it's got the rule book and then it's actually practicing.
Exactly. But even with all that, there's still the aha moment in geometry, those insightful leaps, you know?
Yeah, the aha moments, those are tough. Like, how do you even begin to teach that to a machine?
It's amazing, but the language model, it actually learns to make these, they call them auxiliary constructions, on its own.
Hold on. So it's like it looks at the problem and it recognizes what's missing and then just figures it out.
It's like it has its own eureka moment.
That's wild. So it's not just like blindly following the rule.
It's more like it understands what the rules are trying to achieve and finds its own shortcuts.
Wow. So is that what they mean by dependency difference in the research? Like filling in the gaps in logic?
Exactly. It bridges the gap between pure deduction and that human intuition we were talking about.
That's incredible. So this isn't just number crunching. It's like it's mimicking how we think about these problems.
Yeah, exactly.
Okay, but how does it actually stack up against, real life Olympians?
So they put it to the test, 30 challenging Olympiad problems, and get this.
This is the part I've been waiting for. Lay it on me.
AlphaGeometry solved 25 of them.
25 out of 30. You're kidding. Are you serious? That's amazing.
It's pretty impressive, right?
Impressive. That's unheard of. Okay, but how does that compare to like what a human could do?
It's actually even better than the average score of human Olympiad gold medalists.
No way. So it's like superhuman at geometry.
In a way, yes. And get this, the more difficult the problem, the longer and more complex the proof AlphaGeometry comes up with, just like a human would.
So it's like it's really thinking hard about it, not just spitting out answers.
Exactly.
This AlphaGeometry is seriously blowing my mind, but I gotta ask, how did they even make over 100 million synthetic theorems and proofs? That's insane.
It's a huge amount. It all starts with something called consistent theorem premises.
Consistent theorem premises. Sounds complicated.
It's actually pretty straightforward. Imagine setting up the scene for a geometry problem, like a stage.
Okay, I'm picturing it.
These premises are like the background information. Things like let ABC be a triangle or let D be the midpoint of line segment AB. The key is that they have to be logically sound.
So no impossible scenarios, right? You can't have a square triangle.
Exactly. They had to design a system that could randomly generate these premises without creating any contradictions.
Okay, that makes sense, but how do you even start doing that? It's like teaching a computer to be creative, but within the very specific rules of geometry.
Well, that's where their special diagram building language comes in. Think of it like a set of instructions for the system to piece together different geometric shapes and relationships in a way that makes sense.
So they gave it the building blocks and the rules, and then let it loose.
Exactly. They defined actions like constructing points, drawing lines that are parallel or perpendicular, and even including specific angles and ratios.
Wow, it's like a whole language just for building these geometric setups. But once you have the premises, how do you turn them into actual theorems and proofs?
That's where the symbolic deduction engine, that DD plus AR we mentioned earlier, comes into play. It takes those premises and systematically applies all those geometric and algebraic rules to see what new conclusions can be made.
It's trying every possible combination to see what works.
Exactly. It explores every logical step, branching out like a tree of possibilities.
Okay, so it's exploring every nook and cranny of these geometric setups. But at some point, it needs to figure out if any of those deductions are actually interesting or useful, right?
Absolutely. And that's where the traceback process comes in. Imagine you're navigating a maze.
Okay, I'm in the maze.
You walk through every path, and once you reach the end, you can look back and see the shortest, most direct route. That's what the traceback process does.
So it gets rid of all the dead ends and unnecessary steps.
Exactly. It makes the proof as elegant and efficient as possible.
So it's like trimming the fat, getting to the good stuff. No wonder they ended up with over 100 million theorems and proofs.
Yeah.
It's like a factory of geometric knowledge.
Precisely. And to speed things up, they parallelize the whole process. It's like having thousands of these systems working simultaneously, each one exploring different sets of premises.
That's mind-blowing. They've essentially automated the process of mathematical discovery. But let's switch gears back to AlphaGeometry for a second.
Yeah.
We talk about how it learns from these synthetic proofs, but how do you actually train a language model on this kind of data? It seems very different from, say, training it on text or images.
It is different, but they found a way. They take those geometric statements, the premises, conclusions, proof steps, all of it, and translate it into a format the language model can understand.
So it's like translating from like ancient Greek to English and making it digestible for the AI.
Exactly. And by training on this massive amount of data, the language model starts to pick up on the patterns, the strategies that make a proof successful.
So it's not just memorizing, it's actually learning how to think geometrically.
Right. It learns which constructions are useful, how to combine different geometric rules, and it even starts to develop its own intuition, like we were talking about earlier.
That's incredible. It's like this language model is going from simply crunching numbers to understanding the art of geometry. But what about that DD plus AR, the deduction engine? What's its role in all of this?
It's essential. Remember those auxiliary constructions we mentioned? Those clever steps that can unlock a problem.
Yeah, the aha moments.
That's where the symbolic deduction engine and the language model work together.
Like a tag team.
Exactly. The language model, using everything it's learned, proposes an auxiliary construction like, what if we add this line here?
And then the deduction engine takes over.
Yes. It tests out that new construction, sees if it leads to any promising deductions, and if it hits a dead end, the language model jumps back in with a new idea.
They're like a dynamic duo, bouncing ideas off each other. That's so cool. But tell me, were there any surprises in the research? Did AlphaGeometry ever do something totally unexpected?
Actually, there was. They were testing AlphaGeometry on a problem from the International Mathematical Olympiad in 2004, and during that traceback process.
Yeah, the maze thing, right?
Exactly. AlphaGeometry discovered that one of the premises given in the problem was completely unnecessary.
Wait, the AI is telling the mathematicians they made the problem too complicated?
It's like it was saying, hey, you could have solved this whole thing much easier.
That's amazing. It's like it has a deeper understanding than we do.
It really highlights the power of this kind of AI. It's not just about solving problems, it's about finding those hidden simplifications that even brilliant minds might miss.
It makes you wonder how many other mathematical proofs could be simplified or improved with AI's help. This is incredible.
It really makes you appreciate the potential for AI to shake things up in the world of mathematics.
Absolutely. This is all mind-blowing. We've got AI potentially rewriting textbooks and even schooling us on efficiency. But let's talk about how AlphaGeometry actually presents its solutions. Are we talking pages of dense computer-generated symbols or something we humans can actually understand?
That's another area where AlphaGeometry truly shines. It generates human-readable proofs, presented step by step, just like you'd find in a textbook or a competition solution.
So it's not just about getting the right answer, it's about explaining the logic in a way that makes sense to us. That feels crucial if we're talking about AI actually collaborating and advancing human knowledge.
Precisely. Remember how we discussed the USA IMO team coach evaluating AlphaGeometry solutions? In some cases, particularly for problems from the 2000 and 2015 IMO, those solutions were actually deemed worthy of a passing score, even by human Olympiad standards.
That's incredible. It's not just learning geometry. It's learning to communicate its understanding in a way that's clear, concise, and, dare I say, even a little elegant. But you mentioned earlier that AlphaGeometry's toolkit is still somewhat limited compared to a human mathematician. What did you mean by that?
Well, while AlphaGeometry has mastered a vast array of geometric and algebraic roles, human mathematicians often draw on a much broader and more nuanced understanding of mathematical concepts. For example, a human might use a clever geometric transformation or apply a less obvious theorem that AlphaGeometry hasn't specifically been trained on. That can sometimes lead to a more intuitive or elegant solution.
So it's like comparing, say, a journeyman to a true master craftsman. Both can produce excellent work, but the master has a depth of experience and a finesse that comes from years of dedicated practice.
Exactly. And that's not meant to diminish AlphaGeometry's achievements. These are still early days in the world of AI and theorem proving. The truly exciting part is that this research opens up so many avenues for exploration. Imagine training these systems on even larger data sets that encompass more diverse areas of mathematics, or even incorporating human feedback to help them develop a more sophisticated and nuanced understanding.
It's like we're inviting AI to collaborate with us, to sit at the table and help us push the boundaries of human knowledge. And who knows what incredible discoveries await us on the other side of that collaboration.
Absolutely. If AlphaGeometry, trained entirely on synthetic data, can achieve these remarkable results, imagine the possibilities if we continue to refine its abilities, expand its toolkit, and explore its potential in other domains.
A future bursting with possibilities. From cracking the codes of incredibly complex systems to unlocking the secrets of the universe, AI, like AlphaGeometry, could hold the key to solving some of humanity's most challenging problems.
And what's most exciting is that we're just scratching the surface here. As we continue to push the boundaries of both AI and mathematics, who knows what other hidden patterns, elegant solutions, or even entirely new branches of mathematics are waiting to be discovered.
It's a thrilling thought. By daring to teach machines to think mathematically, we might unlock levels of understanding and innovation that we never thought possible. Well, that brings us to the end of our deep dive into the world of AI and Olympiad-level geometry. We've journeyed through the complexities of synthetic data, witnessed the power of language models and symbolic deduction engines working together, and even glimpsed a future where AI collaborates with us to expand the frontiers of human knowledge.
It's a future brimming with exciting possibilities, and I, for one, can't wait to see what groundbreaking discoveries await us just around the corner.
You know I'm right there with you. And to all our listeners, keep those minds curious, keep exploring, and remember, sometimes the most complex problems lead to the most beautiful solutions. Until next time, happy problem solving.